good morning and welcome to another Grain Talk webinar. Today we'll be talking with Dr. Art Schaafsma about how to improve consistency of DAWN testing results. So Grain Talk, Grain Farmers of Ontario has launched a new way to communicate with our farmer members. We want the important information to be easy to find and recognize. So Grain Talk includes our podcast, our e-newsletter that goes out every Friday, webinars, research days, and our market trend reports. And without further ado, I'm going to pass the mic over to Marty Vermey, and he will introduce Dr. Art.
Hi, Marty Vermey, Senior Agronomist with Grain Farmers of Ontario. I want to welcome everybody here, and especially Dr. Art Schaafsma. You're probably familiar with Dr. Art Schaafsma. He's the Field Crop Pest Management Professor and Researcher at the University of Guelph, Ridgetown campus, and we're happy to have Art with us today. Art's worked on many emerging pest issues that emerged over the years in Ontario agriculture. With Art's foremost knowledge of fusarium in both wheat and corn, Art dove right into the DAWN issue last year with the Ontario corn crop. One of the outcomes was a project to look at the sampling of corn and identify where in the system we're getting all the variable DAWN results. Art will share his findings and we'll have some recommendations for improvement in our testing procedures. Thank you, Art, for joining us today.
Well, thank you very much, Marty and Paige and all those others who are in the background. It's really nice to have this opportunity to share some of the results that we've gathered since the mess happened last fall. So it's been a busy time. A lot of folks have shared in the work. I want to acknowledge Albert and Tanuta and David Hooker and then my chemist, Victor Lima Rios in the lab and a bunch of other seasonal help that helped us with this project. And I also want to acknowledge the funding support that came through so that we could get this work done. And the key funders are listed on the slide at the bottom of the slide. And so I want to just backtrack a little bit and just get everybody on the same page and know what is DAWN. It is a mycotoxin. Myco means fungus, and toxin, well, it means toxin. So it's a toxin produced by fungus. In this case, DAWN is produced by a fusarium fungus. It's also known as deoxynivalenol, and a lot of folks still call it vomitoxin. I just want to remind folks that that's probably a negative sounding word that we might want to try to avoid. We don't need bad press, and so I'm encouraging the industry to try and switch to calling it DAWN, and hopefully that we can all work together towards that. DAWN is regulated in Canada, and so these are the livestock regulations. You're only allowed to include up to 5 parts per million. Milligrams per kilogram is parts per million in cattle and poultry, and swine and young dairy and lactating dairy are more sensitive. And then there's just a comparison there with some of the USA regulations, and you can find this online at the link shown on the slide. What I wanted to do is to share with you that DAWN isn't just DAWN. We're finding there are other things going on, and this has a bearing on the sample kits or the testing kits that we use. And so I wanted to explain just a couple of things about what happens with the fungus and what happens with the plant. And so DAWN has a precursor. There are 2 precursors, 3-acetyl-DAWN and 15-acetyl-DAWN. And there are different strains of fusarium that produce these precursors. The strains that we find in Ontario are mainly 15A-DAWN or 15-acetyl-DAWN strain or precursor producers. And so the fungus then converts the 15-acetyl-DAWN to DAWN. And so when you test the sample at the end, you'll find 15-acetyl-DAWN, you'll find a little bit of 3-acetyl-DAWN, and you'll find DAWN in that sample. And right now, we're mainly just testing for DAWN, and I'll explain to you in the next slide once I get there why it's important to think about these others. And then the plant is also doing something. DON and 15-acetyl-DON are both converted to a glucoside. And what happens is a sugar molecule gets added to them. And what happens is that helps the plant to detoxify the DON and the 15-acetyl-DON. And so it's a defense mechanism of the plant. And so in your sample, you'll also find these glucosides. And they're about 10 times less toxic than their parent compounds. But what happens, we go to the next slide, we know that DON and 15A-DON are about the same in toxicity, and the glucosides are about 10 times less toxic, as I mentioned. But what happens in the gut of the pig, these glucosides or conjugates are broken down and converted back to DON and 15A-DON. So the pig is exposed to the DON that's tied up as well. And so that's something that's important to remember, especially in the feed industry when we're feeding corn and including corn in the feed. And so we sampled a bunch of trucks, 100 trucks, using a tailgate sample, and this is the result of this. And we used a high-end tool called LCMSMS to determine what's in those particular samples. And if you look at the bottom left, percent T-DON, that means percent total DON. And so of the total DON that's there, 75% of it, or 3/4 of it, is DON. About 20% roughly is the glucoside, and about somewhere from 7 to 10% ends up being the 15A-DON. And you can see that the 3A-DON is a very small player. And so keep those numbers in mind. We're looking at about 20%, 20 to 30% of other types of DON in the sample. So when we think of the toxicity of the sample, we need to think more in terms of the total DON and then the other toxins that are in the sample as well. And so when you're feeding pigs, you need to consider the T2 toxin, the fumonisins, and also the zearalenone on top of the other ones we mentioned earlier. So I'm going to approach this talk in the same format as a frequently asked questions fact sheet that we're working on. And so one of the first questions that gets asked is can we use the ethanol process to get rid of DON? Can we break it down in that way? And we did some work a number of years ago already, long before we started having big problems with DON in the ethanol industry. And we tested corn going into the process at on average of 1.8 parts per million in the year 2005. And then we tested what was in the dried distillers grains, and it came out at 5.2 parts per million. And this is about a 3-fold magnification. So what this tells us is that the process doesn't affect the DON. DON is a very stable compound and survives cooking and heating and so on, and survives the fermentation process, and ends up being magnified in the distillers grains, which really affects the quality of that byproduct, which is important to the process and economics. And then going to the ethanol plant, lots of stories. Last fall, I have the same truck load tested. I got rejected and came back, and they accepted it. And so why are we getting these different answers? And this is a very good question. It was a very frequently asked question. And so what we did was we took a sample of corn, and we had three sets of samples where one set was a low amount of DON, relatively low. So in this case, it ranged from, we had 2.5. If you look at the circles on the left, 2.5, 4.1, and 2.8 part per million, more or less a relatively low level. And what we did is we divided that 4 kilogram sample into two 2 kilogram samples. So those are the neck size down circles on the right and the left in 2 columns. So you can see the 2 kilogram and the 2 kilogram. And that represents the size of sample that comes in to the control house at the elevator or the ethanol plant once you've taken a probe sample. And what typically happens is that probe sample at 2 kilograms is passed through a mechanical splitter, and then you get these smaller piles of grain that have been split, and then they take a little cup that takes about 200 grams, and that represents the smallest circle, 200 gram sample, which is then ground, and then a smaller quantity of that flour or the meal is then selected and weighed, usually about 10 to 20, maybe sometimes, depending on the test, 30 grams, and that's extracted with water, and they run the test. And so what we did is we divided that 2 kilogram sample into 10 200 gram samples to represent those smaller samples of whole grain that are taken and then ground. And so the left set of samples are the whole grain split into 200 gram samples and then finely ground, and then the test is run. And then we took the brother sample or the duplicate sample, and then we coarse ground the whole thing, the whole 2 kilograms, before we split them. And then we selected a 200 gram sample of coarsely ground material and then ground it very finely. And so we did this with low DON grain, and then we had 3 sets of samples of middle range DON, around 8 to 10 parts per million, and then we did it again with a grain that was at a higher concentration, high DON, somewhere around 20 parts per million. And what we have here is when we were all done with our extracting and using whatever amounts of flour that we needed, we only use a small amount of the flour, and there's quite a bit left over. We recombined all those samples into their respective constituents. And this particular slide shows you the results of the different lots of grain. And so we have very good agreement between the leftovers of the split samples and the coarsely ground samples. So 2.5 versus 2.5 parts per million, 4.1 versus 3.5, and on down the line. And so what that tells us is that we did a really good job of selecting the sample. It was representative all the way around. Then what we did is we reported the range in DON. We reported some other things, but this particular slide shows you the range amongst those 10 samples that we had of the test results in the low DON level samples versus the mid DON level samples and the high DON samples. And you can see that there was a considerable range and a difference between sample 1, sample 2, and sample 3 within those sets. And then if you compare that to the range when we coarse ground the meal before we did our testing and regrinding, you can see that the range dropped considerably. And so we have a much more consistent result when we ground the entire sample. We could also apply a formula that's in the literature, how to determine sample size. And so what this particular set of data shows on the left, we need a lot of samples to get the right answer within 20% of the true answer. and or to within 25% of the true answer. And what this shows you is that there's a lot of variability between each of those 10 subsamples that we ran. And you would need to, in one case, you need to take 20 of those in order to get the right answer. And that's unacceptable. But then when we coarse ground the material and then divided it into smaller lots, then we can bring it down to only one sample being required. And so it's very clear from these data that we have to try and grind as much of that 2 kilograms that's coming in as possible. In fact, we recommend that you grind the whole thing before you subsample and do your testing. And what we're finding is that this is the most important source of variation in the whole process. It's how much grain you grind before you run the test. Another way to look at this was we took a sample of high DON material that we, you probably remember my tweet earlier in the year, looking for grain that had high contamination. And so we took some of that grain, 20 some odd parts per million of DON in there, and we mixed it with 3 parts of low DON grain. And then we made a lot of grain, 100 kilograms, and it worked out to be close to 10 parts per million. We mixed it, and remixed it. And then we split it, and then took a 20 kilogram fraction and mixed it again, and then took another one and another one. We had 5 lots of 20 kilograms. And then each one of those was again split into those 2 kilogram fractions to represent then a sample that might come in to the control house of the elevator or ethanol plant. This table shows you the results, and what we had were 5 methods of grinding, splitting grain, and so on to see what variation we could try to remove in the process. And so the first method was the old method where we split the grain and then we fine ground 200 grams. And then we, the ethanol plant in Aylmer, IGPC, was taking an initiative, and they basically were splitting 50% of the 2 kilogram sample and fine grinding the whole 1 kilogram of that. And then the what we tried to emulate was the Aylmer IGPC method. We split the sample into 50%, 2 parts, and we started by coarse grinding the first, the whole kilogram, and then taking a subsample and fine grinding it, a subsample of 200 grams of the coarsely ground material. And then the gold standard is perhaps coarse grinding the whole thing and then fine grinding a 200 gram portion of that. And then we think the best way of doing it would be to fine grind the whole 2 kilogram sample, mix it well, and then test. And so what we have here are the results. So again, we had 10 subsamples that we did this with, and so the average result was very close, showing that we did a good job, again, of selecting and preparing the sample. So those numbers are fairly tight, ranging from 9.3 to 10.2. And then the range of results within those tests are indicated here. We had the old way, we had a range of almost 13 parts per million in the results, whereas with the gold standard, we were down to 3.2 parts per million in that result, and that was a much lower range in result. And then we also reported the standard deviation, and again, grinding the whole sample, fine grinding, it gave us the best result, and then again, the calculation of the sample size. So this really supports the idea of grinding a lot more grain than we have been in the past. And the problem we have, though, is how do we grind this? Do we have grinders that do the job and so on? And we're working hard to get to that, because right now that's the bottleneck in the system. The other question that was asked was, does probing a sample with a pneumatic probe or give a representative sample? So is the variation coming from how we take the probe sample? So we looked at this by comparing with a whole bunch of trucks. I can't remember, it was probably close to, I think there's 80 trucks in this result here. And what we did is we stood behind the truck or collected from underneath the truck a grain sample, a little dipper cup going into the stream during the whole unloading of the truck. And then we ended up with about a 5-gallon pail of grain. We ground that whole 5-gallon pail with a coarse grinder, mixed it really well, and then we took a subsample and finely ground it, and then ran our test. And then we had the elevator give us the remainder of the whole grain that they were testing, and that was about 1.8 kilograms, so roughly a 2-kilogram sample. And what we did with that is we divided that into 4 subsamples with a splitter. And then we ground each one of those 4 samples, and then we tested. And this particular graph shows the result of the comparison of the tailgate sample on the bottom axis and the probe sample divided into 4 on the vertical axis. And you can see these numbers cluster into sets of 4. And you can see that these numbers are quite scattered, and so there's a lot of variation when you look at splitting those samples. Now what we did is we recombined those 4 and ran the test again, and this time we have when you think of mycotoxins, this is a pretty good agreement between the probe sample and the tailgate sample. So once you take the whole sample and you run the test, then there's very good agreement. And this was really encouraging. This shows very clearly that the probe sample is not really the problem. It's giving us an adequate sample of the truck load. And basically what they're doing, they've standardized things, 2 probes in the back, 2 probes in the front, and you end up with about 2 kilograms. And so if you stick with that, I think we're in good shape with respect to the probe sample. So yes, the current protocol is doing the job. And then they ask about sampling with hand probes and what constitutes a good sample. It's really important to use a sampling tube like I show here in the slide. We need to get through those layers and sample different layers, because mycotoxins tend to be layered in the load. And so you want to sample vertically to catch these layers. And again, you want to take at least 4 samples, 2 in the front, 2 in the back, and take as many samples as you need to get that equivalent amount of grain, about 2 kilograms. Another question that was asked, my sample was frozen, and does this affect the test result? And the simple answer is no. And how we determined that was we took grain that was at different moisture levels, ranging from 19, you can see that along the bottom, 21, 23, 25, and 7% moisture. And we processed that grain as they would in the control house. And the processing of the grain, the splitting and the grinding and so on, and preparing that sample warms that sample up to within a good range. And so the driest grain with the least amount of moisture ended up being about 17 degrees before testing, and that falls well within the range of doing a good test. My sample was damp, and then what happens is with a damp sample, they obviously adjust the yield according to the moisture, and so they adjust it to a standard moisture, but then they also have to make an adjustment on the mycotoxins. And so by doing a formula or a mathematical formula, is that the same thing as drying the corn and then running the test? And so we did this. We tested this. We tempered some corn to make it at different tests, and we got the same result whether they were tested wet first and then dried and retested. And so you can have confidence in that mathematical adjustment. Does the test weight of corn impact the test result for Dawn? And so what we know here is that higher test weight corn tends to have more hard starch, or the vitreous starch in the kernels, and hard starch often seems to resist Dawn accumulation. And so therefore higher test weight corn tends to have less Dawn. However, the test weight really doesn't affect the result. It just tends to, higher test weight tends to have higher Dawn, but the test performance is not affected by the test weight itself. Another question was, and this was quite a common question early on, is, we're probably finding more Dawn in the dust and in the fines. And if we clean that out, can we affect the test result of the sample? And the other question was, do these fines and do the dust that may sit in the lines and sit in the grinder and so on, can they affect the test result of the following sample, is another question. So we did some work a number of years ago on food grade corn, where we put grain on a gravity table to separate the grain by bulk density, and then we collected the fines at the other end. And so on the bottom of this scale, you'll see the numbers 78, 79, 77, 75, 76, 64, etc. Those are sample bulk densities that came off the table. So the average was of the original sample was 78, and the smallest or the lightest fraction was 64.5. And the black bars show you how much Dawn was in the sample, concentration wise, and the backwards hatched bars show you the percentage of the total Dawn that's in those samples. And you can see that the percentage of total Dawn remains, the most of it still remains in those heavier density fractions, and only a very small percentage of the total Dawn ends up in the fines, even though those fines have a very high concentration of Dawn. Are the test kits accurate and consistent? And so no one had really looked at this. There are a number of test kits on the market. And so what we did is we collected 3 sets of data. One was a check sample survey, where we sent samples to a number of sites. We had 61 returns, and each one of those sites were using whatever kits they were using. And we sent samples, 4 samples, and they were duplicates of 2 different concentrations. One was around 1 part per million, and one was around 4.5. And we wanted to send them in duplicate so we could pick up some variation between test results within a location. And then we took a whole bunch of 40 of these samples that we had sent out, or we retained 40 of them, and we tested them against the 3 main lateral flow test kits. And we tested that against the gold standard of testing that we use, LCMSMS, to see if the results were accurate and precise. And then the other set of samples was we took truck samples, tailgate samples, the same set of samples I showed you earlier, and we tested those against, again, those 3 main lateral flow test kits. And there's a total of 51 samples there. So for the first set of data, with the 2 levels of DON, we also sent those survey samples to 4 different labs to see if those samples were well prepared, and we had very consistent results between the various labs. This shows you what kind of test kits are out there. And so we asked the folks that were doing this to fill in a survey. And one of the things we asked is what kind of test kits are there? And so we basically have 3 companies: Envirologics, which is known as Zygen in Ontario, and Neogen, and our Biofarm. Those more or less have the greatest percentage of the market share. Most of them are lateral flow tests. A lateral flow test is very similar to a pregnancy test. It's basically like a piece of paper that has a little area of antibody on it, and then the liquid, you dip the test in the liquid, and then the liquid runs up the strip and comes in contact with that little area of antibody, and that antibody gets a certain color. The intensity of the color is more or less proportional to how much toxin there is, and you put those little strips in a reader, and the reader determines the color and then calculates the concentration. And they all operate in more or less the same way, and they're all about as easy to use. And so this is a set of data that I found quite interesting. One elevator chain said, well, we want enough kits or enough check samples for 3 locations, and we want to have 2 sets for each location. And so these are the results. And so they were using 1 test kit. And in this case, it was Envirologics, the Quick Tox test kit. And these analysis of variance tables, the most important number to look at is on the far right column, the PR greater than F, the probability of greater than F. Those are important numbers. And if they fall below 0.05, then the effect is significant. And these numbers are all very large. So what we can say without any doubt is there was no location effect. So each location was doing the same job. There was no effect due to the 2 runs. So they got the similar result, and there was no interaction between location and run. And so basically, within that elevator chain, they were getting very consistent results. And their results lined up very closely with ours. The samples were 0.9, 0.8, 4.3, and 4.5 in that table on the right. This is a histogram showing the results of the 2 samples that were sent to each of the elevators with the low concentration of DON. And what we learned, and what I show here, the blue bar is the average between the 2 samples, and the orange bar is the standard deviation on top of the mean. And you can see that when we're dealing with a fairly low concentration, we've got really good agreement between the various locations. There are a couple of outliers. One location was way off, and they're doing something wrong, they needed to. They were advised as to their results, and I think they've corrected what they did wrong. And I don't know what that was, but at any rate, most of them are pretty consistent. So we were pleased to see that. What this is the next set, the two sets of samples that were at a fairly high concentration, and this is where you start seeing more variability. Just to advise you, on the bottom, we have the various test kits listed that were tested at each location. So there was the Dawn Flex, Quick Tox, Reveal Q, Ridgetown, and so on. It also the letter codes, the E's and the N's and the R's indicate the company involved, and then we have the sample number, location number at the bottom. And so that just gives you an idea of the variation. And so we did learn that there are some location to location variation problems. And so there's a need for some training and so on. And interestingly enough, the really tall bar is the same location that had the problem with the low concentration. And so these are a summary of the results showing the various tests, and fairly good agreement. But what we're starting to notice here is that some of the test kits seem to be testing a little bit higher than others. And keep that in mind, and also keep in mind those various other toxins that I was talking about earlier. So now I want to show you the results for the 40 samples that we ran in our own lab. So in this case, I'm showing results for the two main lateral flow kits compared to LC-MS. And so the results, so what you see here is interesting. If you compare the LC-MS for the higher level samples, 4.3, and you look at the Envirologics Donflex kit, it's measuring a 5.4. So it's about 26% different. Whereas the Neogen is pretty much bang on. There's very little difference. And you'll see the same thing happening with the other samples that were of a lower concentration. The LC-MS and the Neogen were very similar, whereas the Envirologics Donflex was testing about 30% higher. And so something to keep in mind as we move forward. And so I'll skip this one because it says the same thing. I'll explain something here. What we have is I've turned that table around from before, and I've added another column which shows the total DON that we measured, all those other DON components. And then if you want to compare the total DON to each of the results, then you can see that the Neogen test is testing quite a bit lower than total DON, but is testing very close to the actual DON, whereas the Envirologic test is testing closer to the total DON than it is to the actual DON. And so the other set of data were from the truck samples, and we compared the three main lateral flow kits from the different companies, compared that to LC-MS. And I'll just show you one of the slides in the interest of time. What this is all the test results plotted from lowest to highest, and we're plotting the LC-MS, which is the light blue line, and so that's the actual DON level. And you'll see that the Neogen line, the dark blue line, is tracking pretty much along with the LCMS. Whereas the Envirologics and the our BioFarm test kits were tracking about 20 to 30% higher all the way along. And another way to look at this data is we plotted the test result for the Neogen test kit on the top left and against the LCMS result. And you can see that in the equation you have, you can see that the coefficient of X is almost 1. It's 0.9987. It's almost 1. So there was a 1-to-1 relationship between the two test results. And the R squared is very high. Anything over 95% is quite high. And so there was very good agreement. So it was accurate and was precise comparing the Neogen test kit versus the LCMS-MS. On the other hand, if you look to the graph on the right, you can see that the coefficient was 0.79. And so what that means is that the Envirologic was actually testing 20% higher than the LCMS pure Dawn test. And if you go to the graph to the bottom right, you can see that if I compared the Envirologics to the LCMS-MS total Dawn, I added all the Dawn components up, you can see that the coefficient is almost 1. And so there's a 1-to-1 relationship. So bottom line in all of this is that some test kits are testing higher, and we believe, and we have a compelling set of data here to show that some kits are cross-reacting to these other Dawn components. So if you're only interested in Dawn, then you'd use, for example, the Neogen kit. If you're interested in the other components, which would be more important on the feed end of things, you'd want to be using the Envirologics and our BioFarm test kits. And another question that gets asked, well, how can you calibrate your lab to make sure you are getting the most accurate result? And most test kit suppliers will also provide you with a check sample. And what that is a sample that has a known concentration of mycotoxin. And at the beginning of every year, every season, you want to get a check sample and test your process to make sure that it's getting the right result. And then you want to do this periodically throughout the season. You'll also want to, and the test kit companies will also provide training at the beginning of each season. So you make sure everybody is doing the same thing at each of your locations and everyone's getting the same result. And this is just good laboratory practice, and the resources are there, and the supplies are there to be able to do this. Another thing that we looked at is can dust be sampled as a surrogate for grain to determine grain concentration of Dawn? In other words, dust is a whole lot easier to sample. You don't have to grind it. You can use a vacuum, and you can sample the whole load from start to finish and have a very representative sample. And so we tested this out looking at samples from 80 trucks from different farm and ethanol plants, and we were comparing the Dawn in the grain versus the Dawn in the dust. And so what we did was we plotted this, and there's about 4 times as much Dawn in the dust as there is in the grain. And we have a reasonably good agreement. We need to do more of this to make sure that we're getting the right answer. But we're fairly confident that this will be a useful tool. And where we see this being useful is particularly on the farm. For example, the grain dryer is finished with a load, And as you transfer it into a hopper, before it gets transferred into another bin, you could vacuum that sample and collect the dust and test it and direct it to the right bin. Or you could load the hopper at the farm elevator before it goes in the truck, and while you're loading it, you could suck the dust out of the elevator. You could put a port in the elevator, and you could suck dust from there while you're loading the whole truck. And then before the truck leaves, you would have a really good indication of what's in your truck. And so that's what we envision there. So I'm getting to the end here. The main sources of variation are listed in red. The ones that we found that are least problematic are listed in green, and the ones that need some attention are listed in yellow. So the probe sample is not the problem. Subsampling of the probe sample that's coming in is the largest, we think, the largest source of variation. Doing a good job of grinding and mixing is also really important, and doing it wrong is also a very large source of variation. The more you extract, and so right now the test kits call for 10 or 20 or 30 grams for 100 milliliters of water. And that's convenient from the standpoint of you have less to throw out and you have less water to use and so on. But that small amount leads to larger errors. And so if you can double that, you would probably reduce your errors by quite a bit. The test kits are not a problem. They seem to be quite reliable. They're accurate. The only thing that we noticed was that some test kits are measuring 20% higher, which we think is related to these other DON compounds. And the test kit, we noticed that there was some variation amongst test kit operators. It's a moderate source of variation and can be easily fixed with some training. So the recommendations we have is educate folks on the probe sample and make sure that everyone's doing a very similar thing. Trying to get people to grind a much larger portion of the grain. If possible, grind the whole sample. Encourage on-site standardized training, and then also educate folks that are using these kits on what the kits are actually reading. And this is a grinder that we're working on. We looked high and low to find a grinder that would quickly grind a 2 kilogram sample. And we couldn't find anything in North America that would at least be cost effective. We could find grinders that would cost you $20,000, but I don't think anyone's real excited about spending that kind of money. This particular grinder we got from China. We had to make some modifications to it to make it safe to use in our lab, but it's a very beefy piece of equipment that does a very good job. And so right now we're working with one of the test kit providers in China. So they have an office in China, and they found the manufacturer, and we're getting modifications made to it, and we're getting it CSA approved. And we hope to bring a number of these into the industry this fall and start a pilot project to see if we can't do a more efficient job and better job of grinding a larger sample. So that's my last slide. Thank you for your attention.
And thank you, Art, for taking us through all of your slides and educating us. We do have some questions here from our team, actually. So I'm going to pass the mic over to Marty, and he will ask you.
Great. If anybody else has questions, you can just type them in the chat area. But Art, one of your earlier slides, I'm kind of wondering about the feed allowable amount of DON between U.S. and Canada. Just wondering if there's any scientific reason why one country would have a different allowable amount of DON than another. It looks like the Canadian one's a little bit more stringent. Are Canadian livestock not able to handle the same amount as Don as U.S. animals, or is there some other reason?
No, and I'm not an expert on this. There is another person who's much more expert. I'll get back to it. I'm going all the way back to that slide. So what the difference is ours is a finished feed, okay, and theirs is intended as ingredients going in to the feed. So basically the same thing. Okay.
Clarity,
So,
I appreciate that. Yeah.
so you understand where I'm coming from?
Yeah, so our allowable is in the finished feed, whereas the ingredients going in, so if it's in corn or wheat, for instance, it gets diluted with all the other ingredients. So you're saying,
right. And so their finished feed, if they went to finished feed, then so ours is actually a nicer system because it allows you to blend things off a little easier. So theirs, you're not allowed to use any grains and grain byproducts that are higher than those limits. Whereas theoretically we could.
that's clear. I understand that much better now. Thank you.
Yeah.
Okay, I'm going to leave the floor open for the chat box for anybody to ask their questions. If there are any questions, feel free to ask them. So we'll just give it a few minutes and then, yeah, we'll
And
go
as
from
other
there.
questions are coming in, I'll just kind of wrap up with some comments and just want to say, Art, thank you very much for giving us an overview. Ontario farmers do appreciate your work that you work in this area of Don and diseases and insects in Ontario, and giving us a better understanding of how we can improve our systems through testing and that to make our end product more consistent and give farmers a reassurance that when they deliver a load into the elevator and when it's done to correct procedures, that they can trust those recommendations that are coming back through the testing. So hopefully that other projects that are undergoing in the upcoming year can help streamline this process and make it easier to do within elevator systems as well as at the farm gate as well. So thank you very much for all the work that you've contributed to in this area.
You're quite welcome.
So we do have one question. Is there any recommendation on sampling crop in a bin, or how many samples to take while filling a bin to get a representative sample for what is stored?
Yeah, that's a really difficult question, and it's hard to pin anyone down on that, including me. And so you have to balance the practicality of it with the idea of taking as many samples as possible. And so just taking a scoop of grain off the top of a bin is certainly not adequate. Probing down into the bin with several probes and ending up with a larger sample that you then subsample is probably a better bet. And so I know it's sometimes difficult to get into the top of the bin. Sometimes the only way you can get in is through a small access hole, and shoving that probe in there is a problem. But just reaching in and grabbing a small sample is not adequate. Setting up, as far as filling a bin, using a small dipper cup and having someone there to take multiple samples into a 5-gallon pail is a good way to do it. And then mixing that pail full of sample and then taking a 1 kilogram sample away for testing is probably important. Now, what I've learned is the labs are also splitting the sample mechanically first and not grinding the whole thing. And I think we need to tell and the problem is it ends up taking more time, and there's more flour and so on to have to dispose of. But I think those labs need to start taking a look at grinding more of that material to get a better test result. We learned that the hard way doing some research. We used to split our samples mechanically, and we were continuing to have numbers that were inconsistent. And so we've now in the last few years have switched to grinding the whole plot. Even though it takes us a lot more work, we get a much better, more consistent answer.
Okay, thank you, Art, for that answer. I want to thank you for joining us. Super informative for all of our farmer members and for those who attended as well.
Quite well.
Thank you to everybody who attended, and have a great rest of your day.